Hi everyone, welcome back to my YouTube channel. This is Raz. In this video, we will continue our discussion about queuing theory and analysis. But in this video, we will focus more on the multi-server system. If you're ready, let's start. So, as a brief recap, in our previous video that we have already, we have discussed the definition of a queue, the relevance of a queuing system analysis in a business and operations, and also some formulae necessary when analyzing a queue, and of course, some basic assumptions and considerations in queuing analysis, especially for single server system. So in this video, we will focus our discussion on a multi-server system. In a multi-server system, there are at least two or more server systems handling this infinite population. So to illustrate, we have these people. These are what we call the infinite calling population, and they will line up, they will fall in line to the two servers in your screen. So they will go to the lines. So this is an example of a multi-server system wherein not just one server is handling the population but also two or more server systems. So in a multi-server models, two or more independent servers in parallel serve a single waiting line. In a multi-server system, it is slightly more complex than a single server queuing system because there is some expansions to the formula that we have already discussed in our previous video. This multi-server systems applies to, real life situations, like for example, at a check-in counters in the airport, or checkout counters in the groceries when you buy groceries, or in the banks, or even in fast food restaurant. Like the single server model formulas, the following assumptions apply in a multi-server model. First, there is an infinite calling population, meaning there is a lot of people queuing or coming into the queue. Second, the line or the queue is served as first come, first served basis. And the arrival rate is Poisson, meaning the customers are arriving in not specific time. They are arriving maybe in 2 minutes interval or 3 minutes interval, and the intervals are not really the same for each of the customers. Maybe for this particular minute, one customer arrives, and for the next 2 minutes, another 3 customers arrive. So it cannot be certain whether how many customers are arriving at a specific minute or time period. We base our formulas on average. And of course, the service rate is exponential, meaning the service rate it should have been greater than the arrival rate, meaning the servers can accommodate people despite the fact that these people are arriving in Poisson rate. It is always a major assumption in queuing theory analysis that the service rate or the server can serve customers faster than the customers arriving. For example, if there are 3 customers arriving in 1 hour, then the server could at least accommodate 3 or more than that. Otherwise, the line would just go infinity. So these are some helpful formulas in queuing analysis. So for multi-server system, the parameters of the multiple server model are as follows. So this symbol, the lambda, represents the arrival rate. This is the average number of arrivals per time period. So this is the number of people arriving on average per hour or per time period. While this symbol, the mu, this represents the service rate. This is a number or average number of people being served per time period. So again, when we say lambda, the first symbol that represents the number of customers on average arriving per time period. While when we say mu, this is the average number of people being served per time period or the service rate. Also, we have this C. This C represents the number of servers. So it could be 2 or more. And also we have the C, mu. This represents the mean effective service rate for the system, which must exceed the arrival rate. So when we say C mu, this is the product of the number of servers multiplied by the service rate. So to compute the probability that no customers are in the queuing system either in the queue or being served is we have P0 or P null is equal to 1 divided by summation of 1 over the factorial of n times the lambda over mu plus 1 over factorial of c times lambda over mu to the power of c times again the c mu over c mu minus lambda. So I know it's a lot to memorize, but later I will show you how is this formula being used in an actual problem or scenario, okay? Just hold on and chill. So another formula is that the probability that n customers are in the queuing system is for n which is greater than c, the Pn is equal to 1 over factorial of c times c to the power of n minus c multiplied by the lambda over mu to the power of n times the p null or p0. But for n which is lesser than or equal to the c, the number of servers, the formula would be pn is equal to 1 over n multiplied by lambda over mu to the power of n times p0. So again, just hold on and chill because we will discuss this formula in our sample problem so that you will not get confused, okay? Another formula that we have is to compute the average number of customers in the queuing system. This is the formula to compute the number of customers being serviced and in the waiting line. So in short, this is the line, the total line. The people waiting in the line plus the number of persons or people in the counter or in the check-in counter or in the server being served. Okay, so the formula will be L is equal to lambda times mu times lambda over mu to the power of c all over factorial of c minus 1 times c mu minus lambda to the power of 2 or squared. Okay, then multiplied by p0 plus lambda over mu. Okay, so oh my god, this is a lot to memorize, but you don't have to memorize all of these formulas. Okay, another formula that we have is to compute the average number of customers in the waiting line. So just what I've showed you a while ago is a formula to use when computing the average number of customers in the entire queuing system, in the line and in the servers being served. So in this case, the average number of customers in the waiting line, and that is LQ is equal to L minus lambda over mu. That's it. Okay, and next you have the average time a customer spends in the total queuing system, like for example being waiting or being served. Okay, so the formula is W is equal to L over lambda. Okay, that's it. Okay, next, the average time the customer spends waiting in the queue to be served, and that is WQ is equal to LQ over lambda. Next, we have the probability that a customer arriving in the system must wait for service, meaning the probability or chance that all servers are really busy because someone is already there waiting. So the new one arriving will have to wait to be served. So the formula will be PW is equal to 1 over factorial of C times lambda over mu to the power of C times the C mu over C mu minus lambda times again the P0. Okay, so let's now have an exercise, an illustration. Again, we will not have to use all of these formula. We'll just try to understand what are these formula or how these formulae work. Okay, so example, we have the lambda is equal to 10 customers arriving per hour at checkout counter, and the mu is 4 customers per hour can be checked out, and there are 3 servicing counters. So again, Before we solve this problem, let's first compute whether the service rate is really greater than the arrival rate. So if we'll compute the 3 service encounters, that is 3, and then the 4 customers who can be checked out per hour, that is 4. So therefore, the service rate or the C mu, that is 12. 12 customers can be served hour by the 3 service encounters. Okay, which is actually good because the customers arriving per hour in average is only 10, which means our service rate is greater than our arrival rate. Okay? So the first thing that we will solve is the probability that no customers are in the queuing system, either in the queue or being served. So we have here our formula as what I have already shown to you just a while ago. Okay, so this is the formula to compute the probability that there is no customer in the queuing system. So we will now replace or assign the values of lambda, the mu, and the n. Okay, we have here P0 or P null is equal to 1 over 1 over the factorial of 0. So before I will continue the assigning of the values, let's focus first in this term. It is said that for this parenthesis, this one, it is the summation of 1 over factorial of n. Okay? And it is said that n is equal to c minus 1 and n is equal to 0. So what does this mean? It means that for the exponents, we should reach or we will reach n is equal to c minus 1. We know that our c or server is 3. Therefore, n is equal to 3 minus 1. So that is 2. Therefore, we should reach the figure 2 as our exponent before we will stop this term. Okay? At the same time, the denominator will start with 0, then plus 1, and so on. So therefore, if we will have n is equal to 2, therefore we will not stop until we reach the exponent of 2 here. Okay, so I will just assign values first here. That is 1 over factorial of 0 times the lambda is 10 and the mu is 4. Then to the power of 0. Again, if our denominator here is 0, then also our exponent here. And since we have not yet reached the 2, which is the n is equal to c minus 1, we will continue our term. So plus 1 over the factorial of 1. So we just add 1 here and also 1 in our exponent times 10 over 4 to the power of 1. Okay, so we'll continue that, adding another term here to reach the n is equal to c minus 1, that is 2. So again, plus 1 over factorial of 2 times the lambda over mu, that is 10 over 4, to the power of 2. And since we have reached already the 2 here, which is n is equal to c minus 1, that is 2, we will now stop the term. Okay? For example, if your c is 4, therefore your n is equal to 4 minus 1, that is 3. Therefore, we will add again another term until we reach the exponent of 3. Okay? So just continue adding until you reach the exponent of 3. Okay, that's it. And then now we go to this another term. So plus 1 over factorial of 3, that is our c, times 10 over 4 to the power of 3. And times 3 times 4 over 3 times 4 minus 10. Okay? So before we go to simplifying this equation, let us first talk about this one. We know that the factorial of 0 is 1. Okay? In our mathematics, we are taught that factorial of 0 is 1. We also know that anything raised to the power of 0 will always be 1. So therefore, this becomes 1 over 1 times 1. Okay? Then here, we know that the factorial of 1 is also 1, like the 0. And anything raised to the power of 1 will be the same. So this means this will become 1 over 1 times 10 over 4. Okay? While here, to get the factorial of 2, we will multiply 1 times 2. And that is 2. So this becomes 1 over 2. Okay? If you are trying to get the factorial of 3, you will have 1 times 2 times 3. Okay? So that is in your mathematics subject. So we will now simplify this equation and we will have 1 over 1 times 1 plus 1 divided by 1 times 2.5 to the power of 1 plus 1 half times 2.5 to the power of 2 plus 1 over 6 times 2.5 to the power of 3 and 12 over 12 minus 10. Then simplifying this all together, we will have 1 plus 2.5 plus 3.125 plus 2.604 and then 6. So this term here, that is 2.604. So you'll just get the cube of this and then multiply by 1 over 6. Then this one is 6. Okay, so therefore, the probability that there is no customers in the queue or in the server, that is 0.045. Next, we have the average number of customers in the queuing system, the customers being serviced and in the waiting line. So our formula is here and we will assign values. So our lambda is 10 and our mu is 4 times 10 over 4 to the power of 3 divided by the factorial of c minus 1, so that is 3 minus 1 times 3, the c is 3 times 4, the mu, and then minus 10 to the power of 2. Then our P0 was 0.045. Then we will add the lambda over mu, that's 10 over 4. So simplifying this all together, so when you simplify, you first begin with what is inside the parentheses, okay? So you just follow the PEMDAS. And then we will get 40 times 2.5 to the power of 3 over factorial of 2 times 2 squared times 0.045 and then plus 10 over 4. So we'll get 40 times 15.625 over 2 times 4 and then times 0.045 plus 2.5. So simplifying this all together, we will get 6 customers in the queuing system. Okay, so this is an average, the number of customers in the queuing system. Then we will compute the average number of customers in the waiting line. So not including the one being served. So our formula is quite simple here. That's LQ is equal to L minus lambda over mu. And we have already computed our L. So that is 6 minus 10 over 4. So therefore, our LQ is 3.5 customers waiting to be served. Okay? And here, the average time a customer spends in the total queuing system. So our formula is W is equal to L over lambda. So W is equal to 6 over 10, and that is 0.60 hours or 36 minutes. Okay? So this is the time that the customer spends in the total queuing system from waiting down to being served. Okay? So now let's compute the average time a customer spends waiting in the queue, not including the time he or she is being served. So our formula is WQ is equal to LQ over lambda, and our LQ is 3.5 over 10, and that is 0.35 hours or 21 minutes. So therefore, out of 36 minutes that the customer spends in the queue, falling in the line and waiting to be served, 21 minutes there out of 36 is spent for waiting in the line. Okay? So that's it. Basically, that's how we compute those complex formulas in a multiple server system. Okay? So now that you have understood how queuing theory and analysis work, so we will now apply this in a real business scenario. Okay, so we have here a sample problem. McDonald's fast food restaurant has a drive-through with a single server who order from an eating. Also is the cashier. The window operator is assisted by other employees who prepare the orders. Customers arrive at the ordering station prior to the drive-through window every 5 minutes, and the service time is 4 minutes. So we are going to determine the average length of the queue and the total queuing time. So remember that the customers arrive every 5 minutes and the service time is 4 minutes. So before we compute the average length of the queue and the total queuing time, remember this is a single server model, and we need to determine first the lambda and the mu, or the arrival rate and the service rate. So it is said that the customers arrive at the ordering station prior to the drive-through window every 5 minutes. Therefore, the arrival rate is computed as 60 minutes divided by 5 minutes. So there are 12 persons arriving per hour. So the other one is the service time, which is 4 minutes. Thus, the service rate is computed as 60 minutes divided by 4 minutes. So the service rate is 15 persons per hour. So again, we should always consider whether the arrival rate is lower than the service rate. That is the most or the basic assumption of the queuing theory and analysis, that the service rate must always be faster than the arrival rate. Okay, and in this case, yes, the service rate is faster than the arrival rate. So now let's compute the average number of people in the queuing line. So our formula, again, if you can recall, in our previous video, for a single server, that is L is equal to lambda over mu minus lambda. So our lambda is 12 over 15 minus 12. So on average, there are 4 persons in the entire queue waiting in the line and in the server being served. So the next is to compute the waiting time, and our formula is 1 over mu minus lambda, and that is 1 over 15 minus 12. Therefore, on average, the customers wait in the entire queue from the falling in the line and then waiting to be served and then being served is 20 minutes. Okay, so 4 persons in the line and 20 minutes in the entire queuing system. So we have here another fact. The management of McDonald's is proposing to reduce the total queuing time through one of the 2 options below. So there are 2 options that the management is considering. So these options would, as proposed, would reduce the total queuing time. So option 1 is to invest in a mobile application called McService, where customers pre-ordered their meals through the app, and a notification will be sent if their meals are ready for pickup. This application requires an initial investment of $50,000 for the app development and the annual maintenance fee of $5,000. With the app, the total service time will be reduced to 1.5 minutes. So remember, the existing service time is 4 minutes. So with this app, the service rate will will be reduced from 4 minutes to 1.5 minutes alone, because the customers will no longer have to fall in line, because they will just order their meals online via the app called Mac Service. And the number of customers arriving per hour will be increased to 15. So remember that the existing system, the arrival rate is only 12 persons per hour, and with this new app, the customers arriving per hour will be increased from 12 to 15. Maybe because it will be faster, so customers will be more satisfied, and a lot of them will be coming in because they can just order their meals online via app. Or the management considers option 2, where in option 2 is to add a new window, where the two windows now can serve at a rate twice faster as the existing. So we know that the existing rate is 4 minutes. So when there will be new window, the 4 minutes will now become 2 minutes, because the service rate will become twice faster. Okay? So this option, however, requires an annual fixed cost of $35,000 and a monthly additional rent of $400. With additional window, the number of customers arriving will be divided equally. However, there will be no change or increase in the arriving customers. So it will still be the same 12 customers. So the management estimated that it will save $12,300 for every minute of reduction in the customer's total queuing time. So which option between 1 and 2 would most likely gain a higher savings? So again, as a recall, the management is considering two options. One is to invest in an app called Mac Service, and with that Mac Service app, the service time will be reduced from 4 minutes to 1.5 minutes. And the other option is to add a new window, where the service rate will become twice faster as existing. So if the existing rate is 4 minutes, then the new rate will be 2 minutes. So we are going to weigh which option would give us a better and higher savings. So first, let's evaluate option 1, that is to invest in a mobile application. And we will compute the new service and arrival rates. So customers' arrival rate with option 1 is 15 persons per hour. So this is the new arrival rate with option 1 being implemented, if implemented. So the total service time will be reduced to 1.5 minutes. Therefore, the service rate now is 60 minutes divided by 1.5 minutes, so that is 40 persons. So from 20 persons in the existing system, the 20 now with the mobile application will become 40. Okay? So it can serve twice as many customers. Okay? So now let us compute the new waiting time, the given data. So the waiting time is computed as 1 over lambda over mu minus lambda, and our mu is 40 minus 15. Therefore, with this mobile application, the waiting time will become 2.4 minutes in the entire queue. So from 20 minutes waiting in the line, waiting in the queue as what we have computed in the previous existing system, it now becomes 2.4 minutes. So from 20 to 2.4, therefore, it saved 17.6 minutes. Okay? So that is a lot. That is a lot of savings. Okay? So from 20 minutes, it is now 2.4 minutes, because of course the customers would not have to wait in the line. They will just order their meals through the app, and then they will just be notified whenever their meals are ready for pickup, and they will save their time. And since the service is faster, of course McDonald's would get a lot of savings from that. It would save cost, it would save time, it can serve more customers. Okay? So we will now evaluate whether this is worth an investment. So therefore, the savings, that is $12,300 times 17.6 minutes saved. So for the total year, McDonald's would save $216,480. Okay? However, of course, we will deduct the cost because having this mobile application, it has to spend some investment, and that is $50,000, and the annual maintenance fee of $5,000. Therefore, the total net savings under option 1 is $161,480. So that is a lot. So what do you think? Is this a good option? Let's find out for option 2. Under option 2, to add a new window, we will compute first the new service and arrival rates. As we know, there will be no increase in arriving customers. Thus, our existing arrival rate of 12 persons will be the same. Nothing will change. Okay? But the service rate will be 2 times faster because of the new window. Thus, service time from 4 minutes now becomes 2 minutes because it becomes faster. Okay? So the service rate is 60 minutes over 2 minutes. Therefore, it can serve 30 persons per hour. From 15 persons per hour, now it can serve 30 persons per hour. That's times 2. Okay? So, again, we'll compute using the new waiting time using the formula. This formula. 1W is equal to 1 over mu minus lambda. So that is 1 over 30 minus 12. So the new waiting time under option 2 is 3.33 minutes in the entire queue. If we're going to compare this with option 1, we know option 1 will give us 2.4 minutes. So this is something that, higher than the option 1. So from this given computation alone, you might say that, option 1 is better than option 2. But before that, let us first compute how much would be the savings. Maybe option 2 will give us a surprise. Okay? So under option 2, from 20 minutes previously computed, it now becomes 3.33 minutes. So that is 16.67 minutes saved. In option 1, that's 17.6. But in option 2, that's 16.67. So, as we know, option 1 really has a higher number of minutes saved. But let us find out if option 2 will give us a shocking result. Okay? So, therefore, the savings under option 2 is $12,300 times 16.7 minutes, and that is $205,000. And to have this new window, the management has to pay for the annual fixed cost, that is $35,000, and to pay the additional monthly rent of $400. So that's 400 times 12, that's 4,800 per year. So therefore, our net savings under option 2 is $165,200, which is actually a lot higher than option 1. Because under option 1, it would only save us $161,480. So therefore, between option 1 and option 2, though the time saved is higher than in option 1, but as to cost, as to money-wise, as to savings, option 2 is better. Therefore, if you are the management, which option would be more beneficial to you? Of course, option 2. So that's it. That's the application basically of queuing theory and analysis. So in queuing theory, our goal, our focus is to reduce the waiting time, because customers waiting too long in the queue are customers not satisfied with your service. Okay, so that's it. Thank you so much for watching,